In this video, we're going to take a look at directional derivatives. So we're going to take derivatives in specific directions. Now, we've already taken the partial derivative of a function on R2. In other words, where our inputs are coming from a set in R2. So f of xy. And we've taken the partial derivative of f with respect to x. That's f sub x. Remember, that was basically, we were letting x be our variable and fixing the y as a constant. So how is my function changing as x is changing? That's what f of x is telling me, or f sub x, excuse me, is telling me. Same thing with partial derivative of f with respect to y. I let y change and let my x be fixed. And f sub y is telling me how y is changing, or how my function is changing as y changes. All right. So the partial derivative f sub x gives us how the function changes as x changes. The partial derivative f sub y gives us how the function changes as y changes. Now, what does a directional derivative do? It says, well, what if my y and my x are both changing? And what if specifically they are changing in a specific direction, in the direction of, let's say, a unit vector in R2? So if I have my function, which is a continuous function with inputs from R2, then the directional derivative of f at point xy in the direction of u is denoted this. It's denoted by a capital D sub vector u of f, and it's the limit. And what we do is we change both the x and the y in the direction of our unit vector u, and we let h go to 0. So this is essentially saying x and y are changing at some angle. How is my function changing if both x and y are moving along in this direction, in this unit vector direction? Now, the limit definition isn't that useful for us. What's going to be useful for us is the actual directional derivative equation here. So we start with that exact same assumption that we have a continuous function on a set in R2. We have a unit vector. By the way, it is very important that we're using a unit vector here. If I use a different vector, I need to make sure I need to scale it so that it becomes a unit vector. But the directional derivative of f at point x0, y0 in the direction of u is going to be f sub x at that point times u1 plus f sub y at that point times u2. The u1 is the x component of my unit vector. The u2 is the y component of my unit vector. So that's the directional derivative. And again, note what the notation is here. It's capital D with a subscript u, and then the f comes behind that. So derivative of f in the direction of u. Derivative of f in the direction of u. F sub x times u1 plus f sub y times u2. So let's take a look at this example. We're going to find the directional derivative of a function x squared minus 2x plus y squared minus 3 in the direction of the vector 1, 2 from the point 1, 0. Now, we've looked at this function before, and we've actually started at that point before in previous videos. But here we're looking for the directional derivative in the direction of 1, 2 from the point 1, 0. Let's go ahead and do the calculations for that. Now, a couple things. This vector, 1, 2, is not a unit vector. So I'm going to want to create a unit vector. We'll call it u in that direction. If you remember how to do this, we take 1 over the magnitude of u, or the magnitude of the vector, times the vector, and that'll give us a unit vector. So 1 over, let me just write the steps down this time, 1 over u, vector u, magnitude. Actually, I'm sorry. Let's call this vector v. I don't want to get it confused. Let's say this 1, 2 is vector v. So 1 over the magnitude of that vector times the vector itself gives me a unit vector in that same direction. Now, the magnitude of this is the square root of 1 squared plus 2 squared. That's the x component squared plus the y component squared. So that's 1 over the square root of 5 times 1, 2. So that's going to be my unit vector. I'm just going to write it this way. In the direction of 1, 2. Now, there's my unit vector. The other things that I'm going to need are f sub x, which in this case is 2x minus 2, and f sub y, which in this case is 2y. We've calculated that before. If you're having trouble with partial derivatives, go back and look at some of the previous videos we've done. Now that we have f sub x and f sub y, since we're looking for what those things are at the point 1, 0, in other words, since I'm looking for my directional derivative at the point 1, 0, well, the directional derivative at the point 1, 0, actually, let me do the at the point x comma y first, is f sub x times u1. In my case, actually, let's do this. I'm going to write the most general version first. So f sub x at whatever point we're at times u1 plus f sub y at whatever point we're at times u2. So that's the idea. That's my directional derivative. Technically, this u should be a vector u. Let's see if we can accent that correctly. There we go. So that's my directional derivative in general. And if I'm plugging in the point 1, 0, then I plug it into my first derivative with respect to x, and I'll plug it into my first derivative with respect to y. And then in my case, u1 is the number 1 over square root of 5. And U2 is going to be the number 2 over square root of 5. Excuse me. Now, let's check this out. F f sub x at 1, 0, if I plug in 1 for x, 0 for y, I get a 0 in my f sub x. So I get 0 times u1 again. F sub y at 1, 0. Well, if I plug in 1, 0 in for y, I plug in a 0 for y, I get a 0. So my directional derivative at the point 1, 0 is actually just the 0. I get 0. So my directional derivative at the point 1, 0 in the direction of u is going to be 0. By the way, the reason that is because as x is moving and as y is moving, there's 0 change as you move in the x direction, 0 change as you move in the y direction. So in any straight line path, my derivative is going to be 0 at this point. Now, at other points, we could get different values. So if you plugged in something other than 1 comma 0, you are going to get a different directional derivative. So basically, this is what's going on. Here's our actual function that we're looking at. I think that's the function. And what we have, if you remember, our f sub x and f sub y gave us vectors that were tangent to the graph in the direction of the x-axis and in the direction of the y-axis, respectively. So f sub x was in the direction of the x-axis, f sub y was in the direction of the y-axis. And basically what we're doing is we're creating a linear combination of those two vectors. And my directional derivative is going to be going in the direction of, well, if you look at it here, I've done in the direction of 1, 2. Notice that we're going 1 in the x direction, up 2 in the y direction. So that's the directional vector, 1, 2. And so in the xy plane, as you look straight down, it's going in the 1, 2 direction. And you're saying, well, how much change in the z direction are we moving? What's the slope of z? And at this particular spot, there's no change because the f sub x and f sub y are both essentially not giving me any change in z. So these are completely flat with respect to z. So that's the idea. You were getting this linear combination of the f sub x and f sub y in a certain direction. And that direction in our case was in the direction of the vector 1, 2. And we kind of see how that goes. Again, this is not my exact directional derivative vector. I've scaled this up a little bit so that you can see it a little bit easier. Otherwise, we'd have a unit vector pointing out here. So I have scaled it up just a little bit. But linear combination, and you're saying how much change in z is there in this direction? Well, in that direction, there's no change in z. Let's take a look at another example. So we're going to have the same function, but we're going to find the directional derivative of that function from a different starting point, from the point 3, 0. And we're going to find the directional derivative as we go from the xy coordinate of 3, 0 to the xy point -2, -4. So I want to find my directional derivative from this point to this point. So a lot of this, we'll use a lot of the same work that we dealt with last time, since this is the same function, although we're at a different point and we're going in a different direction. Now, first off, the thing I want to find is the direction that I'm going. Well, actually, it doesn't matter what you do first. You could find the unit vector first, or you could do the first derivatives with respect to x and y if you'd like to. I'm going to find the unit vector first. And so first off, I want a direction. If I start at 3, 0 and go to -2, -4, well, going from 3 to -2 is going down 5 units in the x direction, and going from 0 to -4 is going down 4 units in the y direction. Now, that's the direction you're going, -5, -4, in the direction of that vector. Now, if I want to make that a unit vector, I take -5 squared, that's going to give me 25, plus -4 squared, that's going to give me 16. And I'm going to take 25 plus 16 all under the square root, and that gives me square root of 41. So the unit vector in the direction I want to go is this vector here, scalar 1 over square root of 41 times the vector -5, -4. Hopefully that's not too much. We're just going from this point to this point. So initial point is 3, 0. Terminal point is -2, -4. That gives me this vector here. Now, once we've done that, let's take f sub x. F sub x, we've already calculated, is 2x minus 2. F sub y is 2y. Again, the directional derivative is going to be f sub x at whatever point we're at, multiplied times u1 plus f sub y at whatever point we're at, multiplied times u2. Again, u1 is the first coordinate of my unit vector. u2 is the second coordinate of my unit vector. We wanted to be at the 0.30. So we're going to plug in the 0.30 into all of that. 30 into my directional derivative. Well, f sub x, when I plug in 3, I get 2 times 3 minus 2. That gives me a 4. So f sub x at 30 gives me 4. U1 is -5 over the square root of 41. We've already established that. Plus f sub y at 30. Plugging in 30 into f sub y, I would get a 0 times, well, u2 would be -4 divided by square root of 41. And when that's all said and done, my directional derivative in the direction of u at the 0.30 becomes -20 divided by the square root of 41. Now, if you take 20 divided by the square root of 41, that's about 3.12. I should say approximately here. About -3.12, excuse me. And so it's saying that if we start at 30 and we go in the direction of u, in other words, if we go towards the point -2, -4, we get a slope of -3.12 roughly. All right, so this one's going to be a little bit harder to see, but it's still doable. So we're starting at the 0.30. In fact, if you plug in 30 into my original function, I get the 0.300. So we're right here. My f sub x can be represented by this purple vector. My f sub y can be represented by this other purple vector. And so it's saying as this point moves towards the 2, -4, that's moving in this direction in 2 dimensions. So as we move, whoops, as this point moves that way, this point moving that way, this point moving that way, what's going to happen? Well, as this point moves towards here, we actually should go down. And initially, the initial direction is down. And if you look at this is in the same plane as our f sub y and f sub x, same plane. And this blue directional derivative vector has slope, and it says as we move towards this green spot over here, again, I just made that like a vertical line so you can see it easy. As you move in that way, the slope, we're moving down as at a slope of about 3.12 units as I move in that direction. So as you move that way, we're moving down negative, what was it, 3.12 units. Hopefully that makes sense. So going that way, moving down, it's not quite the same as this, but it's a linear combination of f sub x and f sub y, and that's what we're getting. Now, one thing I do want to kind of show is that this might seem weird because if you actually look at what's going on, the point -2, -4, when you plug that into your original function, you get a point way up here. So you may think, well, if I want to go from the actual point 300 to -2, -4, whatever this z value is, I need to move up. But remember, we're moving along the curve in this direction. So what's happening is that we're moving along this vector, and that's forcing us to go across the curve, across this surface in a specific motion. Let me explain what I mean by that. So if I follow this purple dot, if I look straight down, let me, if I look straight down along this purple dot, we're moving in that direction. So we're moving specifically in that vector direction, okay, of -5, -4. But as it moves, it's also moving vertically. So what's happening is that this purple dot, as it starts moving towards that direction, it hits this, and it has to go down along the curve, and then it'll turn and go back up. So initially at this point, we're going down and then back up. Excuse me, I mistyped something. I knew something was going on wrong. So we need to go down and then back up along this curve. So that's why this initial blue vector here is pointing down. It's because as you move along the curve, I hit that point, I'm moving in the direction -5, -4. At that point, we're moving down, and then eventually it turns back up. So initially we're going down there. If I'm moving in the two-dimensional space across. All right. So I'm start going straight across from 3, 0 towards -2, -4. And it goes down along my curve. And it's going down, obviously, initially here at slope negative. It's going down at a slope of -3.12, roughly. So these are kind of my two examples of finding directional derivatives. I could give a direction with a certain vector from an initial point like 1, 0, or you could start at an initial point and go towards another point and say what direction, what is the change of z, instantaneously change of z, as I start here and move towards this. So you can go from point to point or from a point in a directional vector. Now, another concept we're going to look at is the concept of gradient. The gradient is a vector, and it's essentially the vector f sub x comma f sub y. Obviously, we want to have a differentiable function in order to have a gradient. Otherwise, it doesn't work. And gradient is always denoted by delta f. Remember that delta, we're talking about that upside down triangle here. That's what we're talking about. Yeah, by delta, I mean the upside down delta. Hopefully we caught that. So upside down delta or just upside down triangle of f is f sub x comma f sub y. All right, that's the gradient of my function f, as long as we can get those. So let's calculate the gradient of our function that we've been dealing with so far. We have our function x squared minus 2x plus y squared minus 3. Let's calculate the gradient of that. All right, so I'm going to shorthand my symbol. Again, upside down delta f or triangle f is equal to f sub x comma f sub y. Again, I'm shorthanding what I'm doing here. And then my f sub x, we've already calculated that. That's 2x minus 2. My f sub y, we've already calculated that. That's 2y. So that's my gradient. My gradient is the vector whose first component is 2x minus 2 and whose second component is 2y. Now we can calculate the gradient at various values. For instance, if I want to find the gradient at the point 1, 0, well, I'm just going to plug in 1 into x, 0 into y. And if you do that, we get the gradient at 1, 0 is the vector 0, 0. The gradient at point 3, 0 is what you'd get if you plugged in 4 for x. I mean, 3 for x, so you get a 4 as the first component. And then a 0 would be the y component. So you'd get 4 comma 0 as your vector. So that's the gradient. And we can see how that matches up with everything we've been doing so far, all of these partial derivatives. And now we have a vector that's called the gradient vector of f. Let's calculate another gradient. Here we have a different function. So let's find the gradient of this function. The function of x and y is equal to sine x times cosine of y. So we'll find the gradient here and take a look at it. And while we're doing that, let's go on to the next one. The next one I'm going to take and find the gradient of another function, y times e to the 3x. So we'll do both these functions at once, both example 4 and example 5 without flipping back. So example 4, the function is sine x times cosine y. Example 5 is y times e to the 3x. Let's look at both of these. So we'll start with my first function here, sine x cosine y. The derivative with respect to x is going to be my first component of the vector. The derivative with respect to y is going to be the second component of my vector. So the gradient for this particular function, if I take the derivative with respect to x, derivative of sine x is cosine of x. So I get cosine of x multiplied times cosine of y. That y is a constant with respect to x. So cosine of y is also constant with respect to x. Now, if I take the derivative with respect to y, the sine x is a constant. Sine of x is a constant. The derivative of cosine of y will be negative sine of y. Again, this is with respect to y. I'll put the negative out front. So we get cosine x times cosine of y, comma, negative sine x sine y. That's the gradient of f. And if I want to find that at any point, I could just plug in the x and y at that point. Let's take a look at my other function, y times e to the 3x. Again, we're just taking the derivative with respect to x and the derivative with respect to y. So my gradient vector in this case, if I take a derivative with respect to x, I get e to the 3x times 3. So I get 3y e to the 3x. That's the derivative with respect to x. The derivative with respect to y, well, e to the 3x is going to be constant, so I just get 1 times e to the 3x. So that's my gradient in this function, f sub x, comma, f sub y. And again, if you want to plug in any point, you could plug in any point you want to. Now we may ask ourselves, why do we care about gradients? Why would we ever want to calculate a vector when we already know f sub x and we already can figure out f sub x and f sub y independently on our own? Well, there's a connection between a gradient and a directional derivative. In particular, if I want to find the directional derivative of f in the direction of vector u, which is u1 comma u2, it's going to be the dot product of the gradient of f with u. If you think about what f is, it's f sub x times u1. When I do a dot product, it's f sub x times u1 plus f sub y times u2. So I get the dot product of the gradient and the unit vector. That tells me the directional derivative in the direction of u. So now we can employ some tools for dot products when we're dealing with directional derivatives. So let's do an example. Let's use the gradient to find the directional derivative of the function f of x comma y at the point P in the direction of vector 5 comma 8. So I'm going to use gradient to do this. We've already done a similar thing with just calculating f sub x and f sub y independently. So let's do this with gradients. All right, so we are starting at P of 1, 1 and going in the direction of 5, 8. Now, obviously, the vector 5, 8 is not a unit vector, so I'm going to make that into a unit vector by taking 1 divided by the magnitude of 5, 8. That's going to be 5 squared plus 8 squared. So that's 25 plus 64, all underneath a square root. That's the magnitude of that vector, 5, 8. 25 plus 64 is 89. And that's 1 over the magnitude here, 1 over the square root of 89. And then I'm going to multiply that times the vector 5, 8. So times 5, comma 8. Might as well just do another line. 1 over the square root of 89 times vector 5, 8. There we go. So that's the unit vector in that direction. Now the gradient we know is f sub x comma f sub y. And we've already calculated f sub x and f sub y for this function. F sub x is 2x minus 2. F sub y is 2y for this function. Now the gradient at point 1, 1 is going to be a vector. So the gradient at point 1, 1, let's go ahead and gradient of f at point 1, 1 is going to be the vector. Well, what's going to happen when you plug in 1 into the x component? You get 0. When I plug in 1 into the y component, I get 2. So that's the gradient. So if I want to find the directional derivative at the point 1, 1 in the direction of this v, I can take a dot product. I can take my directional derivative, oops, in the direction of u at 1, 0. That's going to be my gradient dot producted with my vector u. But specifically, in this case, the gradient at the point 1, 1 dot producted with the vector u. So that's going to be vector 0, 2 dot producted with vector, well, I'm going to distribute this 1 over square root of 89, so that's going to be 5 over the square root of 89 comma, and then 8 over the square root of 89. Okay, so it's the dot product of those two vectors, which is pretty clear. We're going to get 0 times 5 over root 89. That's going to give you a 0. And then 2 times 8 over square root of 89. That's going to give me 16 over the square root of 89. Okay. So that's the directional derivative of f. Oh, I'm sorry. I mistyped here. That should have been at the point 1, 1 in the direction of u. So that's the idea. By the way, that's about 1.70 if I round it to 2 decimal places. It's just under 1.70. But there you have it. So directional derivative in the direction of u of f at point 1, 1 is equal to about 1.70. And that's telling us something about the slope as we move in the direction towards 5, 8 from the point 1, 1. Let's go visualize that real quick. So here we are once again looking at our same function. That surface. What's going on here is that, again, purple is the directional derivative. This time, the purple that's sticking up is the directional derivative in the y direction. That's f sub y. That's giving you this slope, that purple slope. F sub x is the one that's pointing, in this case, to the left. And then if you think about the directional derivative, its slope is giving us 1.7. That's telling me as I start at this point, which is at the point 1, 1. By the way, that's 1, 1, negative 3, if you're interested. And you're moving in the direction of 5, 8. Going to be hard to see, but in the direction of vector 5, 8, we're going that direction. Again, hard to see, but we're moving over 5, up 8. So we're pushing in that direction. Well, then my z value is changing by a slope of about 1.7 at that point. Okay. And again, as you follow a point as it goes along here, whoops, there we go. Maybe that was going a little bit too fast. So here I'm starting at the negative. As my point is traveling in the direction towards the direction of vector 5, 8, it hits this point and then it's traveling up along the side of that surface. So going in that direction initially. Going in that direction initially. Okay, that's the idea. And so that's telling you how much z is changing as my point goes in a specific direction. And in this case, as my point goes in the specific direction of towards, well, in the direction of vector 5, 8, my z is changing by about 1.70 per unit of change. That is this unit vector of change in this direction. Hopefully that makes sense. Let's do another example. Here we have example 7. So we're going to take the function sine x times cosine of y. We've already found the gradient of that in a previous example. And so we're going to look at what happens, how much change in the z value there is, change in the output, if we are at the point pi over 3, comma 3 pi over 4, and moving in the direction of vector 1, comma 1. So let's calculate this. Okay, so here we go. Like I said, we've already found the gradient. So the gradient is cosine x cosine y, comma, negative sine x times sine y. And we're looking at the vector 1, 1. Now, again, as always, I have to be very careful that I get the vector in that direction, in the direction of 1, 1, but I need the unit vector in that direction. So I can't just take 1, 1. I'm going to have to take 1, 1 times 1 over the magnitude of that vector. The magnitude of that vector is going to be the square root of 1 squared plus 1 squared, which is the square root of 2. So that's my unit vector. Now let's deal with the gradient. Well, the gradient of f at the point pi over 3, comma, 3 pi over 4. Well, let me just go ahead and plug that into the gradient. So cosine of pi over 3, cosine of pi over 3 times cosine of 3 pi over 4. Make sure your mode is in radians. Anytime we're doing calculus with trig functions, we want to use radians. If you calculate that, you get an ugly decimal. But it is doable. First off, cosine of pi over 3 is a half. Cosine of 3 pi over 4 is, depending on how you write this, it's either square root of 2, negative square root of 2 over 2, or negative 1 over square root of 2. So I get 1 half multiplied times the square root of 2. Oh, shoot, I forgot to put the negative out front. Negative square root of 2 over 2. So that's what we get when we plug in those two values into the cosine x, cosine y. Cosine of pi over 3 gives me 1 half. Cosine of 3 pi over 4 gives me negative root 2 over 2. Now let's do the same thing for sine. First off, I have a negative out front, but sine of pi over 3 is going to be root 3 over 2. Sine of 3 pi over 4, and I'm just typing this into my calculator, is a positive root 2 over 2. And so I'm going to simplify that a little bit just so I have some nicer vector to deal with. That's going to be negative square root of 2 divided by 4, comma, negative square root of 6 divided by 4. So that is my gradient at that point. If I want to find the directional derivative of my function in the direction of u, I'll leave off the arrow, at this specific point, at pi over 3, comma, 3 pi over 4. So the directional derivative at that specific point, I just take the dot product. So the dot product of 1 over dot product of u, let me write that because I'm gonna, so that's my u, 1 over square root of 2, comma, 1 over square root of 2. If I multiply 1 over square root of 2 by square root of 2 over 4, negative square root of 2 over 4, I'm going to get negative 1/4 when I multiply again, first component here times first component there. When I multiply first component here, second component here times second component there, I get a negative, well, root 6 over root 2 is going to give me square root of 3 over 4. So basically what I'm getting is negative 1 minus the square root of 3 divided by 4. I can type that into my calculator. When I do that, I get about a negative 0.68. So that means if I'm at this point and moving in the direction of vector 1, 1, my z value, my instantaneous rate of change for my z value is about negative 0.68. I won't graph this one, but you can kind of get, hopefully you got what's going on from the previous examples. Again, change in z is about negative 0.68 if you're at this point and moving in direction of u. Let's do another example. Here is example 8. We want to find the directional derivative, and we're going to be at the point 0, 4 and moving towards the point 3, 6. And we're going to use the gradient to find that. Now, the function is y times e to the 3x. So we've already found the gradient, the general gradient. And now we're going to go, again, start at the point 0, 4 and move towards the point 3, 6. All right, so again, previously we've already found the gradient. The gradient of f is 3y e to the 3x, comma, e to the 3x. So I won't do that again. We want to find how z is changing as we are at point 0, 4 and moving towards point 3, 6. So that means we are moving in a vector direction, which is, well, change in x's, we go from 0 to 3, so that's an increase of 3. Change in y values, we go from 4 to 6, so that's an increase of 2. Now, that's the directional vector. In order to find the unit vector in that direction, I'm going to take the vector 3, 2 and multiply it times 1 over the magnitude. 3 squared plus 2 squared is 9 plus 4. So 1 over the square root of 9 plus 4 is 1 over the square root of 13. So that's my u. And if you want to rewrite that, you can rewrite that as 3 over square root of 13, comma, 2 over the square root of 13. Again, magnitude of 3, 2 is the square root of 3 squared plus 2 squared. So square root of 13. Now, I have my vector here that is my gradient. If I'm at the point 0, 4, then that gradient of f at the point 0, 4 is going to be vector that I get when I plug in 0 into x and 4 into y. So I'd take 3 times 4 times e to the 3 times 0. That'll be my first component. My second component will be e to the 3 times 0. So my gradient at the point 0, 4 is going to be 12 comma 1. 3 times 4 is 12. E to the 0 power is 1. So 12 times 1 is 12. And then e to the 0 power is 1. So what that means is that the directional derivative in direction of u of f at the point 0, 4 is going to be the dot product of my gradient at 0, 4 with the unit vector u, which means I'm going to take 12 times 3 over root 13. 12 times 3 is 36. So we get square root, 36 divided by square root of 13. And then I'm going to take 1, multiply it times 2 over root 13. That's just 2 over the square root of 13. So my directional derivative at the point 0, 4, as the point goes towards 3, 6, is going to be 38 divided by the square root of 13. Now, 38 divided by the square root of 13 is about 10.54. And so if we are at the point 0, 4, and we begin to move towards 3, 6 in the direction of this unit vector, we go 1 unit in that direction, it's going to look like it changes the z direction by 10.54 units. Change the z value, not z direction. Change the z value by 10.54 units. So the z value is going up. The slope of that tangent line is going to be about 10.54. Now, gradient is nice, but in terms of the amount of work, it's not that much different in terms of the amount of work to find the directional derivative by just using f sub x times u1 plus f sub y times u2. So if we use the formula f sub x times u1 plus f sub y times u2, it's really not any less calculations than doing the dot product of the gradient with the unit vector. However, being able to see gradient dot producted with a unit vector as our directional derivative of f in the direction of u allows me to use some of the features of the dot product. In particular, if you remember, if I take the dot product of two vectors, that is the magnitude of each vector multiplied times cosine of the angle between them. Since my u is a unit vector, that means that the dot product of the gradient with the unit vector u is going to be the magnitude of the gradient times cosine of theta, where theta is the angle between the gradient and the unit vector. Now, what does that do? Well, this, remember, was derivative. So this tells me something about the interplay between the derivative and the angle between a direction we're traveling and a gradient vector. Remember, cosine of theta, cosine is going to be a maximum of 1 and a minimum of -1. Therefore, this derivative is always going to be less than or equal to the magnitude of the gradient at any given point. That happens when cosine theta is 1. And the smallest value we can get is the negative of the magnitude of the gradient. And that happens when cosine of theta is -1. And obviously we can get cosine of theta to be 0 too. So how does this impact my surface, my three-dimensional surface? Well, it shows us what direction we should move to have the greatest change possible, what direction we should move to have the smallest change possible, and what direction we can move in to give us no change at all. What direction is that? Well, when, again, theta is an angle where cosine of theta is 1. By the way, we should all know that cosine of 0 is 1. Then if the theta is 0, then we get our maximum. If theta were pi, we'd get -1. That's the smallest change or biggest change in the negative direction. And if theta is pi over 2, we get no change whatsoever because the cosine will be 0. So here's what it comes down to. Let's assume that we have a function which is differentiable with gradient, this upside down delta f, at some point. The maximum value of the directional derivative at the point x0, y0 happens, so the maximum z increase is happening at the gradient when I've plugged in x0, y0. And the maximum value will be the magnitude of the gradient when I plug in x0, y0. So the direction of maximum increase is the direction of the gradient. The minimum value of the directional derivative is going to be negative the magnitude of the gradient. And the direction of minimal increase is going to be negative whatever the gradient is. And at a point, the gradient, excuse me, sorry about that. Had to clear my throat. So at the point P, the gradient is going to be orthogonal to the level curve passing through x0, y0, z0. Z0 is just the z value of the function when I plug in x0, y0. That's what I mean by z0. Okay. So we get a maximum value of the directional derivative that happens at the direction of the gradient. We get the minimum value of the directional derivative happening at the negative direction of the gradient. And then orthogonality happens with the level, the gradient is going to be orthogonal to the level curve passing through the point x0, y0, z0. So let's take a look at example 9. Let's use the gradient that we found earlier and use the point 1, 1. With our function that we started with earlier, x squared minus 2x plus y squared minus 3, and we are going to find the direction of maximal increase of the function at p, and that's the maximum value or the maximal value of the directional derivative at p. We're going to find the direction of minimal increase at p, and then we'll find a direction such that the directional derivative is 0 at point P. So we're going to find all 3 or 4 of those things. So previously we were at the point 1, 1 and going in the direction of 5, 8, and we found the directional derivative in the direction of V, that is 5, 8, came out to 1.70. That's probably not going to be the maximal increase. So if I want to find the maximal increase, what I do, so find the direction of maximal increase. Well, the direction of maximal increase is going to be in the direction of our gradient at the point 1, 1. We've already found the gradient. We've already found, again, upside down delta of f. That was 2x minus 2 comma 2y. And so the direction of maximal increase is going to be, again, upside down delta of f at 0.11 is going to give me vector 0, 2. Now, 0, 2 is the direction of maximal increase. Obviously, that's not a unit vector, but it does tell me the direction of maximal increase. And the maximum value, well, the maximum value of my directional derivative is going to be, or at this P, obviously, I should have said at the point P, is going to be the magnitude of my gradient. Which is 2. 0 squared plus 2 squared, all under square root, is 2. Magnitude of 0, 2 is 2. Now the direction of minimal increase, or maybe the direction of maximum decrease, some people would say, is simply the negative of my gradient at the point 1, 1, which is fairly straightforwardly going to be 0, comma, negative 2. And the maximum decrease value is going to be negative 2, or the minimum value of my directional derivative in the direction of u of my function f at my point P is going to be the magnitude of my gradient and then negate that. So it's going to be negative 2. So minimum value is negative 2. Now let's give a direction such that, oh, I keep doing that. I keep saying you. Hopefully you guys understand that we're talking about the vector u and not just a numerical value, but the vector u. If we want a direction such that there is no change in my function, well, what are we going to do? If you think back about it, we know we're asking ourselves what dot product with the gradient is going to be give us 0. And hopefully you remember how we can do that. We can take a vector in R2, which is orthogonal, and in R2, what I can do is I can take the gradient vector, which is 0, 2, swap the X and Y values, and then negate one of them. So I could either have negated the 0, or I could have let U be -2, 0. Both of those are going to be orthogonal to my gradient. And maybe I should have said direction of a unit vector. I don't know if this has to be a unit vector. It was kind of ambiguous in the way the question was asked. Obviously, this is not a unit vector, but this is a direction in which we'd get 0 as our directional derivative. Here's another direction where we would get 0 as our directional derivative. If I wanted to make those into unit vectors, I would just multiply by 1 over the magnitude. In this case, that's magnitude is 2. And so if I wanted a unit vector, it'd be 1, 0 or -1, 0. So either one of those is orthogonal to the gradient vector, and therefore each of those is going to be such that if we move in that direction, we're moving 0 units in the y direction. Now, before I move along, I did want to point out something, that we already went in a specific direction. We went in the direction of vector 5, 8. That is not in the direction of the gradient, but that's not in the direction opposite of the gradient either. So that's just in some direction. And notice that my directional derivative was 1.70, which came under my maximum value of 2, obviously. So we can get a maximal change of 2, or a minimum value of -2. We can get a 0, and we can get basically anything between -2 and +2, essentially. And the one I had tried earlier got me to about a change of 1.70. So again, maximum change that's possible is 2, and our change in Z was about 1.70 from earlier. So let's take a look at what we're saying here. Here's our graph of our function with the tangent vectors of f sub given by f sub x and f sub y. So f sub y, partial derivative. If you change y, you're moving in this direction. If you change x, you're moving in this direction. And notice that what we were told is that if we're moving in the direction 0, 2, we're getting maximum change. If you think about what that means we're moving in a direction, a vector, which is parallel to the y-axis. So if we're moving in the direction of the y-axis, that gives us our maximum change. If we're moving in a direction parallel to the x-axis, we're getting no change. That was the 2, 0 vector, giving us no directional change. that should match up with what we see here. The maximum change is when I'm going straight up. I'm taking this point and I'm moving it straight up this elliptical paraboloid. And when I'm moving across left and right in the direction of x, I'm getting no change. So left and right, I don't mean in all directions, I mean in the x direction. So I'm getting no change if I'm moving in the x direction. I'm getting maximum change if I'm moving in the y direction. Hopefully that makes sense. And obviously the change if I'm moving down at this point, if I'm moving down, that's the maximum value of negative change, maximum and absolute value. So the minimum directional derivative value at this point. So maximum and minimum change are happening along this angle, and then no change would be happening if we moved along in the x direction, either left or right. And that's what this is telling us. Maximum direction of increase is in the direction 0, 2. Maximum value of increase is 2 units. Minimal increase is in the direction 0, negative 2. Minimum value of increase, or minimum value of the directional derivative is negative 2. And then if I want no change, then I move in essentially the x direction. And I can move either left or right in the x direction to do that. Hopefully all this making sense. Let's do another example. Let's use the gradient to find the following things for the given function at 0.04. The function is y times e to the 3x. That's a good function because we've already found the gradient of that in previous example. We want to find the direction of maximal increase. What's the value of maximal increase of so what's the maximum value of the directional derivative? I want to find the direction of minimal increase, and then we'll also find the minimal value of the directional derivative. And then we'll find a vector such that the directional derivative is 0 at point P. So we'll go and do that for the 0.04 and this function here. Like I said, we've already found the gradient of this function. Y(e) to the 3x has gradient 3y(e) to the 3x, comma, e to the 3x. So that's the gradient. And earlier we said, well, if we're moving towards Q, that gave us a directional derivative of about 10.54. So that's the instantaneous change in Z measurement. Again, that's starting at the same point of 0, 4. Starting at a different point, we'd get a different value. So we want to find the direction of maximal increase direction of maximal increase is going to happen at the gradient of f at the point 0, 4. If I plug in 0, 4, I'm going to plug in 4 for y and 0 for x. I already did this earlier, but I might as well do it again. I already found this specific gradient earlier, but I'm going to do it again. I am ending up with 12, 1. So that's the direction of maximal increase. If we're traveling towards, from point P in the direction vector of 12, 1, I get maximal increase. That's the direction of maximal increase. The maximum value is just the magnitude of that gradient vector. So that's going to be the square root of 12 squared plus 1 squared, which gives the square root of 145. That's just slightly over 12. Again, notice that's the maximum value is slightly over 12. So obviously we didn't touch that in our direction, but we got fairly close. Our direction earlier. Now the direction of minimal increase is just going to be the negative of the gradient, again, upside down delta of f, 0, 4. And that's negative 12, negative 1. And the minimum value of the directional derivative is going to be, well, the negative of the magnitude of my gradient. So it's the magnitude of the gradient, but take the negative of that, which is negative square root of 145. All right. Let's make sure we got the accent properly. Okay. Now, if I want a direction of a vector such that the directional derivative is 0 at P, all I have to do is take some vector. I'm going to use V instead, just so I don't get it confused with the unit vector. So I'll go my vector V. Well, maximum happens at the gradient. So I want something that's orthogonal to that. So we switch the X and the Y components, the first and second components, and then negate one of them. Or I guess I could have taken the negative of that same vector. Again, switch the X and Y components. And then now we're negating the other one. So there you go. If we go in that direction, the gradient direction, that gives me my maximum value, my maximum change. If I go in the opposite of the gradient direction, I get my minimal value for change, and I get no change when I go in an orthogonal direction. Now again, these are not unit vectors. If I want to make these unit vectors, I just multiply by 1 over the magnitude. It doesn't specify that this vector has to be a unit vector though, but a lot of times we make it a unit vector. So if you want to make it a unit vector, just 1 over the magnitude of this, which is, by the way, 1 over square root of 145. So if I want to make this a unit vector, all I have to do is take 1 divided by the square root of 145. That's the magnitude of that vector, and then times the vector. So there you go. That's how we can find the direction of maximum change, the direction of minimal change, and the direction of no change. Now, all of our functions so far have been two variable input functions. So we've input an x and a y, and we've gotten an output, which is our z. And those are nice because they allow us to sort of visualize in 3 dimensions what's going on, maximum change, minimum change, and so on and so forth. If we have 3 variable inputs, then we can do a similar thing. If I have a function whose input is a subset, or whose inputs are coming from R3, and if I have u as a unit vector in R3, then the gradient of my function is the vector f sub x, f sub y, f sub z. And the directional derivative of f in the direction of u is going to be the gradient dot producted with the unit vector u. This is exactly the same concept that we had earlier, except now I'm throwing in a third dimension, a third component to both my gradient, and obviously my unit vector has to be a unit vector from R3, not from R2. Now, interesting enough, maximum value here. Maximum value of the directional derivative is also going to be the magnitude of the gradient, and it's obtained when the gradient and the direction I'm going in have angle between them, which is 0, which essentially means that they're parallel, right? They're the same thing, or because we're using a unit vector, this unit vector is just going to be the scalar of the gradient. The gradient vector scaled down to have length 1. So when the angle between them is 0, which means that they're parallel. And so the direction of maximal increase is the gradient vector, and we get the maximum value by taking the magnitude of the gradient vector. In the same vein, the minimum value of the directional derivative is the opposite of the magnitude of the gradient, and it's obtained when the gradient and the direction of travel have angle between them of pi, because cosine of pi is -1. And that means essentially they're going in opposite directions. So the direction of minimal increase is the opposite direction of the gradient. And we get directional derivative of f in the direction of u to be 0 whenever the gradient and u are orthogonal. So we can do a very similar thing. And again, this all comes from dot products and what we know about dot products. This rule for dot products doesn't just work in R3 or just on R2. It works in R2, works in R3, works in R4 too. So we can do that. And then obviously cosine of theta, it's maximum when it's 1. That means when the angle is 0. It's minimized when the angle is pi, because that gives you -1. And if the angle is pi over 2 or 3 pi over 2, then we end up with a cosine of 0. So that dot product becomes very handy finding the maximum value for the directional derivative and finding the minimum value for the directional derivative, finding the direction of maximum increase, finding the direction of minimum increase, and then finding where there's no change. So let's do an example. Let's find the gradient and the derivative of the following function, f of x, y, z, excuse me. There you go. F of x, y, and z is equal to x squared y minus y squared z. We're going to figure that out at the point 1, 4, 3 and in the direction of v. So we'll find the gradient, we'll find the directional derivative at this point in this direction. All right. We might throw in maximum direction of maximum increase and all that stuff too. So first thing, we want to find the gradient. So we want to find the gradient of f. That's going to be the vector f sub x, comma f sub y. Why do I keep doing that? Comma f sub z. All right. So gradient is going to be derivative of with respect to x, derivative of f with respect to x is going to be 2xy plus 0, essentially. Derivative with respect to y is going to be x squared minus 2yz. And the derivative with respect to z is going to be 0 minus y squared, or just -y squared. Now this means if I take the gradient at the point 1, 4, 3, it's going to give me a specific vector. Well, if I plug in 1 for x and 4 for y, the first component becomes 2 times 1 times 4. That's 8. The second component becomes 1 squared minus 2 times 4 times 3. That gives me a negative 23. And then last, when I plug in 143 into the third component, I get negative 4 squared. That's negative 16. So that is the gradient at 143. Now, the unit vector in the direction of v is going to be 1 over the magnitude of v. The magnitude of v is the square root of 1 squared plus 1 squared plus 0 squared. That's the square root of 2. Multiplied times the vector 1, 1, 0. So there we go. So if I want to find the directional derivative in the direction of u of my function f, I can take the dot product of the gradient and this unit vector u. So I'm talking about at specifically the point 143. By the way, you can find this in general too by using x's and y's instead of plugging in numbers. But if I take 8 times 1 over root 2, I get 8 divided by square root of 2 plus negative 23 times 1 over square root of 2 is going to be a negative 23 over the square root of 2 plus negative 16 times 0 over the square root of 2 is 0. So the directional derivative of my function in the direction of u at point 143 is going to be negative 15 divided by the square root of 2. Now that's about negative 10.61. So that's the directional derivative of my f at point 143 in the direction of u. Now, again, we could have talked about maximum change. The maximum that your directional derivative could be for any u, so for any u, maximum directional derivative is going to be the magnitude of f. And if we're talking about at the point 143, that is going to be the square root of 8 squared plus negative 23 squared plus negative 16 squared, which is 8 squared plus negative 23 squared plus 16, negative 16 squared. That's the square root of 849, it looks like. Again, that's approximately 29.14. Okay, so the maximum directional derivative you could possibly get is 29.14, and that's if my vector u was in the direction of my gradient at the specific point, 143. So in other words, if my u was in the direction of 8, negative 23, negative 16. Okay. We can do the same thing with minimum. Minimum directional derivative. I'm going to actually just copy and paste this. So the minimum value for my directional derivative would be if I got a negative of the value of the gradient, which would end up as negative about negative 29.14, or exactly negative square root of 849. And that would happen if u was in the direction of the opposite of the gradient. So in the direction of, let's say, negative 8, positive 23, positive 16. Now, if I wanted a directional derivative to be 0, I could simply pick a u that was orthogonal to this vector, this gradient vector. And there's lots and lots of options for that. I won't go through picking one right now, but if you remember how to do that, you can essentially just pick anything for your first component, anything for your second component, and then solve for your third component. We use dot products to do that. So we can do that. There's other methods as well. If you want to think about it, now I've talked myself into doing an example. So let's find a u so that the directional derivative in the direction of u of f is 0 at this point, at the point 143. One easy way you could do this is you could take 8, negative 23, 16, and I'm just going to give a 0 for the third component. I'm going to switch negative 23 and 8, and then I'm going to make one of them the opposite value. So I'm going to get 8 times 23 plus negative 23 times 8 plus negative 16 times 0 when I do a dot product, and that all adds up to 0. So if I let my u be that, swap the x and y, let the z value be 0. And when I swap the x and y, I make sure one of them I change the sign on. So swap the x and y, change the sign on one of those, make the z value 0. There is a direction of travel that gives me 0 change in my directional derivative. So there you go. I know we were only asked to do this part, find the directional derivative, but I ended up doing all of that as well. Let's do another example. Let's take my function, and that function is in 3 dimensions, sorry, f of x, y, and z. So my function is f of x, y, and z is equal to 6z over x squared plus y squared at the point 1, 1, 1 in the direction of v of 0, 2, 3. So we'll find the gradient and the directional derivative in this direction. And then, knowing what we know, we'll find direction of maximum increase, direction of minimum increase, and we'll find orthogonal direction as well, one where my directional derivative becomes 0. So we'll do all that for this particular function. All right, so the first thing we're going to have to do, well, I can do one of 2 things first. I can find the unit vector in the same direction as v, or I can start taking derivatives of my function f. So let's find the unit. Actually, let's do the derivatives of my function f, because that's going to take a little bit longer. If I'm taking derivatives of f, what I'm going to look at with respect to x and y, I'm going to rewrite this as 6z times x squared plus y squared to the negative 1. And when I take my gradient, derivative with respect to x is going to be 6z times x squared plus y squared to the negative 2nd power times the derivative of the inside function. This is with respect to x. So with respect to x, I get 2x. So 6z times 2x becomes 12xz times this whole thing to the negative 2 power. We're going to do a very similar thing when I take a derivative with respect to y. I have 6z out front. I do x squared plus y squared raised to the negative 1 power. And the negative 1 gets reduced. And then I multiply times 2x out front. 2 times 6 is 12. So I get, oh, sorry, not 2x, 2y. Sorry, with respect to y, my f sub y. So with respect to y, derivative of the inside function is 2y. Now the nice thing is when I do the derivative with respect to z, this x squared plus y squared to the negative 1 is just a constant. So I just end up getting 6 times x squared plus y squared to the negative 1 power. We can figure out the gradient at the point 111 right now by just plugging in 1 for x, 1 for y, 1 for z. 12 times 1 times 1 is 12 multiplied times 1 squared plus 1 squared. That's 2 to the negative 2 power. Similar thing for my second component. 12 times 1 times 1 is 12 times x squared plus y squared. That's 1 squared plus 1 squared to the negative 2 power. And then for my last component, I get 6 times 1 squared plus 1 squared to the negative 1 power. Now, don't get too thrown off by these negative powers. 2 to the negative 2 is just 12 divided by 2 squared. So that's 12 divided by 4. So I get a 3. Again, 12 times 2 to the negative 2 power, that's 12 divided by 2 squared. That's again a 3. And then 6 times 2 to the negative 1 is just 6 divided by 2, which is 3. So the gradient is 3, 3, 3. The unit vector in the direction of v is going to be 1 over the magnitude of v multiplied times v itself. So v itself is 0 to 3. The magnitude is going to be the square root of 0 squared plus 2 squared plus 3 squared. That's 0 plus 4 plus 9. So that's square root of 13. All right, so if we're going to calculate the directional derivative in the direction of u of f at the point 111, I can just take a dot product of 3, 3, 3 with this unit vector. So dot product 3 times 0 gives me 0. 3 times 2 divided by square root of 13 gives me 6 over square root of 13. And then 3 times 3 over square root of 13 gives me 9 over the square root of 13. Six plus 9 is 15, so 15 divided by the square root of 13. That's the directional derivative of my function at point 111 in the direction of u, or in the direction of v, which is 0, 2, 3. Fifteen divided by the square root of 13 is about 4.16. So there you go. Now we've already calculated the gradient at this point. So the direction of the maximum directional derivative is going to be the gradient at the point 111 in this case. That's the vector 3, 3, 3. So that's the direction of the maximal directional derivative we could obtain. And the max value of the directional derivative at that point is going to be the magnitude of this vector. So we get 3 squared plus 3 squared plus 3 squared, all underneath the square root. That's 9 plus 9 plus 9 underneath the square root. I guess I can. So we're taking the magnitude of my gradient at the point, and that is going to be the square root of 27. 3 squared plus 3 squared plus 3 squared. If I want to do the minimum, well, the direction of the minimum directional derivative is going to be when u is the negative of the gradient, which is -3, -3, -3. And the minimum value we can get is the negative of the magnitude, which would be -27. By the way, negative square root of 27. And that's negative about 5.20. And if I'm looking for a u, so that my directional derivative, whoops, should have just did that, is 0, then we just need to pick an orthogonal vector to this gradient. And one such vector for u is going to be the vector, well, again, we'll swap the x and y's and put a 0 in z, and then make either the x a negative or the y a negative. So I swapped the 3 and the 3 since they're the same, they look the same, and then I made one of them a negative. If I do that, I'm going to get an orthogonal vector to my gradient, and therefore the directional derivative of f in the direction of that vector will give me 0. So there we go. Again, we can check that pretty easy. Now that we have our gradient of 3, 3, 3, just do a dot product with -3, 3, 0, and you'll see that you do get a 0, right? And that's what your directional derivative is. The dot product with your gradient and your unit vector u. So we've seen a lot of calculations with directional derivatives. These directional derivatives give us how much the output is changing when we're moving in a specific direction, not just in the x direction, not just in the y direction, but we're moving at a specific vector direction, a specific vector angle. How much is our output changing as I move at a specific vector angle? And visualizing this stuff in R4 is really tough. So again, I'm going to go back to one of the previous ones we did where we said that if you're moving from point 30 in the XY value along this surface in, and we're moving towards green, towards that green dot, so we're moving here, how does my point move along this surface? If I'm going from here towards there, how do we go through the surface? Well, the surface, we're going to start moving down. So as I move in that direction, the point moves down, point moves down, and then eventually it'll move back up. But at this specific value, the point is moving down, and at what angle? Well, at this rate. So it's going down at this rate, and so that's changing my z by some obviously negative number that we calculated earlier. So going down at that angle as you move from this point over in that direction. I hope this video helps with your understanding of directional derivatives. Remember, directional derivatives are this, which can be written as gradient times vector u. But in essence, it's some sort of a linear combination of your derivative in the direction of x and your derivative in the direction of y. So some combination of moving x and y at the same point, or excuse me, at the same time in a specific direction. So it becomes a linear combination of those first order partial derivatives. So this is the end of the directional derivatives video. I hope that all of this made sense.